Okay, hello, welcome. Six or seven lecture. Um, Next week is Hanukkah. We will not meet. There is a homework that I will release in a day or two, which will be for 3 weeks instead of two, so you don't have to work in Hanukkah. But if you want, you can use Hanukkah to work on it. Okay, that's it. So we did the Dijkstra and started the DLG last week. Today we're going to actually do DLG and then hopefully mostly concurrent in the second hour. Okay, so DLG, we had problems with Dijkstra that it was not perfect. So we had that free list traversal, which is easily solved. We talked about this, and we just use a blue color. But the rest of the topics we'll cover now step by step. So let's do this. So eliminating the free list scan, we said we're just going to add the blue. So each object that's in the free list, it's kind of waiting for allocation. It's free. The allocator knows that it can allocate this space, so it's blue. This is the color that we'll use. So another item that we need to cover is what is the color of a new object. So now we take something blue and allocate it and put it into the use of the program. So what color do we give it? So if we just allocate it white, it can be reclaimed. If we do it in a moment where the collector doesn't notice it and then sweep comes, it will be reclaimed, which is not good. We do not want to reclaim objects that the program is using. That is very important. That is the most important thing for correctness. So during marking, we want to put it black, which is always good because it's alive now. We've just allocated it, and so we want it black so it will not be reclaimed during the sweep. But we also it has no children, so it is okay if it's not gray. It's black. We don't need to scan it. If there will be new children, a write barrier should take care of it. But right now, it is alive with no unscanned children, so it can be black. So that's what we want. We could do gray, but then each allocation would bring more gray objects, and we want to be able to be done with all the gray objects so we can finish the tracing part. And so we prefer black. During sweep, now this is, here there is a bit of a race. So what happens is if we have the heap, right? And when we're sweeping, there is a kind of, let's call it swept pointer. There is a pointer which we go over the heap, and for any black object, we just make it white. If we see a white object, we reclaim it. So if we're here and the swept pointer still is supposed to see this object, we want it black. We want it to be noticed as alive and become white. But if it's here, then we want it white because we don't want in the next collection to start with a black object. Black objects are really bad for the next collection. To start a collection with a black object means that we're not going to scan its child, so its children. So it's really, we don't want to have a black object at the end. So if we're here and we'll do it black, it will be bad. If we're here, we want to do it black. And so during sweep, it depends on the object location. We want it white if the area was already swept, this object was already swept, and we want it black otherwise. Okay, but this is not easy. So this is what we want to have. So in the allocation, if phase is marking, we just want it black, that's fine. Else, if it is sweeping, then if the address is before sweep, the swept pointer, then we want it white, and otherwise we want it black. So, and sweep, of course, if the object is black, then we want to make it white. And if it's white, then we want to reclaim it. We want to move it to the free list. So this would have been nice if this pointer was not moving all the time. But since it's moving, then we do not. So we check the pointer. So there is two problems. One of them is that. So one of them is we can check if the phase is marking, but until we actually do the blackening of this object, it may happen that we're already in sweep because the phases are changing while we work. And DLG will make sure that we'll not move from sweep to mark without noticing, but we can move from mark to sweep. And if we move from mark to sweep, then we may in the beginning do the check, the test, and see that it's marking. But then when we actually come to do the operation, it will already be sweeping. This is bad. So this is phase value is outdated when we actually do the color change. And the other thing is that sweep pointer, this pointer is advancing. So one thing that we know, if we're here, if swept has already gone after us, then it will not change. This is stable, right? It's only moving that way. But if we're here, then we don't know. Maybe we check the sweep pointer, we find that it is before us, and therefore we want to do it black. But then when we actually do it black, maybe the sweep pointer has gone after us, and then we do wrong. We keep a black object for the next collection, which will be really bad. So these are races. So we have two races like this, and we have to solve them. So the first thing we note is that it's always safe to mark, to do gray objects. If we allocate objects and they become gray, then it's always okay. Because in the worst case, we will not reclaim this object now, and it will be gray in the next collection, but in the collection after that, we'll be able to reclaim it. So there will be nothing incorrect. We'll only have some objects that will remain for more collections. So the way that DLG solve this, they say, if the phase is marking, then we make the object black. However, we check again. If the phase has changed after we did it black, it changed to sweep, then we don't want to leave black objects there. We just set it gray. This is a case that happens seldom, right? It happens when we check during the mark phase, but then we discover that it has moved. The collector has moved to sweeping after we did it. So then we make a modification and we just put it gray. Gray is always safe. And as for the sweep pointer, we check the address. If the address is smaller than the sweep pointer, then this is not going to change. The sweep pointer just becomes larger and larger. So it will always be higher than the address of the object, and then we can make it white. Otherwise, we're in a race, we don't know. We are here, and the sweep pointer may or may not pass us as we do this color selection, and we just make it gray. This is what DLG suggested, and this is correct. Okay, there may be gray objects, maybe too many. Maybe you could have saved more objects that you could make not gray. If it is gray, it is correct. Everything is okay, but it will remain for the next collection. It will be gray then, and it will be marked, and all its children will remain in the heap, even if it's not alive anymore, if it's not reachable. But it's not incorrect. So it will just delay the time where this object is going to be reclaimed. Okay, so this race and the solution is fine.
This only works because the garbage collector notifies when we move from sweep back to mark.
Right, I have to talk about this. I will, that we never go from sweep to mark without noticing. Yes, this is important for this. Okay, so another topic. We want to avoid repeated heap traversals. So originally in Dijkstra, they said, let's look for a gray object and then, trace its children and make it black. So looking for a gray object throughout the heap is very expensive. If for each gray object we have to go through the entire heap, heaps are large. We don't want to do that. And then, so even Dijkstra say in his paper that you shouldn't do this in real life. You should have some list of gray objects. And if you make an object gray, add it to the list. And if you need a gray object, just go to the list and get it from there. So there is always in any production, any real garbage collector, there will be a list like that. It's called a mark stack. It will be a stack of objects. And so IBM took DLG and did it in Java in a practical collector. Then they used the mark stack. And later we'll talk about the implementation, but there is like a stack where I put, whenever I create a gray object, I put it in the stack. Whenever I need to trace a gray object, I take it from the stack. I don't go over the entire heap to look for a gray object if I need one. So, and if you have like a collector, mutator, maybe several program threads that access this stack, you have to have a mark stack or a list or whatever that is robust to parallel accesses. So someone inserts, another guy inserts something into the mark stack, and someone takes an object from the mark stack. You have to make sure it works with parallelism. That is not a problem. We know how to do it today. We'll not talk about implementing concurrent data structures in this course, but there are courses on that in our faculty, and you can learn them. But we assume that we have a stack that can work with parallel accesses. Okay, so that's it. If you have any questions about this should be clear. Okay. So another thing is that we had a single thread. Okay, that is not reasonable for programs today. Programs use all the cores. They work with multiple threads. We want to work with multiple threads of the program. So with Dijkstra, we had two options: either to change the pointer and then mark it gray, or to mark it gray and then change the pointer. And we saw that each of them had a problem. So Dijkstra chose the first one, and it worked correctly for a single thread. And he had to do like a good analysis in order to make sure that everything works well. And it only worked for a single thread. It doesn't work if you have two threads. So so Dijkstra uses so DLG is going to use the other option. Let's recall what the problems were. So with change and shade, we had a problem that the invariant of no black to white object did not work like in between, and we had to analyze it better. But with change and shade, we had the problem. Here is the problem. We had the problem there was a very long write for the program. And this write first shaded the child that was getting a pointer. So suppose this is the modification. Like this is the old referent, this is the new referent, and this is the parent. Okay. So our problem is that we changed this pointer and we worry that this is black. It is like an object that we have scanned and we have scanned its children and we're not going to scan it anymore. And this object is white, so we haven't seen it. And it's going to be under an object. It's going to remain reachable because it will be reachable from here, but we're not going to scan again this object. So this was our worry. And so this shading, if I shade the child, if I shade this before I make the change, then the shade, this gray color may be lost if the garbage collection moves to a new phase. So if the program shades the child, makes it gray, and then the marking is done, it makes it black, and then sweep makes it white, and then a new marking begin, and only then the actual modification is done, but this is by now white because the sweep has made it white. So if we have this long write of the program and a new collection, where now the marking phase is seeing this, and it might be a black to white edge that no one protects. There's no shading anymore going on because the shading is already gone. So what DLG said, we're going to use shade and change, but we're not going to let the collector change to a new garbage collection phase without the program, while the program is writing, is having this long write. So we're going to put this like in between. Before I start a new marking phase, I'm going to make sure that no program thread is in the middle of a write. Okay, so I'm going to coordinate a new collection. Let's look at the picture. There are these quantifiers. I need each thread to not be in a long ride, right? It shouldn't have a ride that it's persisting between one collection to another. So here, suppose I'm finishing sweep and starting mark, and the question is whether this picture is okay or not. So I need that there will be no thread that has a persisting write that goes from one collection cycle to the next collection cycle. Is this okay or there is some bad? So which thread is not okay? 3, right. So this could be a write that goes from the previous cycle to the next cycle. What I need is that each of these threads will finish a write before I start the new marking phase. So this is not good. So it's okay for here. There is a write that finished. There's no long ride that's persisting between cycles. You know, this one is finished, this one is finished. I don't need them to finish at the same point in time. I just need to make sure that each of them does not have a persisting write. So if I do this, if I start the mark here, is this okay? I wait and I start it here. Yeah, you're right. So all threads, no thread has a long write from the previous cycle to the next cycle. If you look at this, there is a break. For this guy, there is a break before I start. For this guy, there is a break. So each of them has finished a write before I started the mark. He didn't have a write that lasted from the previous cycle to the new cycle. So this is the thing that we want. And let me go back. So the solution is to coordinate a new collection with the program threads. And before starting a new collection, I want to ensure that no mutator has a persisting write that goes from the previous cycle to the next cycle. And the easiest solution is to say, just stop all the threads when no one is in the middle of a write. And then I know that no one has a long write that from the previous cycle to the next cycle. But this has a cost. So what happens is if you stop the thread and you want to make sure that all of them are in the correct place, you need to do it somehow. So you could stop all of them and then find that one of them is in the middle of the write and just let it go until it finishes the write and then stop it again. There's this coordination takes time until you have all the threads together. No one is in the middle of a write. It takes time, and this has a cost. So we prefer not to have it. Sometimes we'll have it because it's complicated not to have it, but the way to ensure that you don't have anyone in the middle of the write is to use handshakes. So the handshakes, the collector says, it raises some flag and says, I want to start marking, and now I want each of you program threads to tell me that you're not in the middle of a write, that one write has completed. Uh, so each mutator responds to that flag by raising its own flag. So the collector has a flag, and each program thread has a flag, and the collector starts by raising its flag, and then one by one, the mutators raise their flag saying, we finished the write, I finished the write, I finished the write. When all of them finish writing, then the collector can start a new phase. Okay, this is a handshake, and what you see here is in the second thing is the collector waits. So when it starts, the collector raises its flag, and then this guy can respond immediately. This guy can respond here and say, "I'm not in the middle of a write." This guy has to wait until here to respond and say, "I'm not in the middle of the write." But when everybody has responded, we can start a new mark phase. Yeah. Yeah, all of them can continue. You respond only once, here the flag maybe rose. You respond once and you can continue then to work with no problem. This is not interfering with the program work. It just responds and goes on working. It's
You're not using a scheduler, but you're reacting to what the program
yes.
does, changing how the
Exactly. The way it is done in real life is that whenever you go back in a loop, you check if you need to respond, and that happens all the time. And whenever you call a function, it's just inserted into your program. When you go back in a loop, there is some test. Does the collector want to start? I'm not in the middle of a write. I will respond. Or if you call a method, then I check, did the collector ask for a response? If yes, I will say yes, I'm not in the middle of a write. So once in a while, you check if you need to respond as a program thread, and then you tell the collector, I'm not in the middle of a write, you can go on. And I'm going on working. I don't have to stop. So this guy, for example, maybe it responded here or here, but it went on. It doesn't need to wait for anything. So the handshakes are the collector stops and wait, but the program just goes on working as if everything is okay. Just responding and going on working. Yeah. Okay. Cool. So handshakes means that you don't have to stop all the mutators together, which is good, which is very good. And the handshakes also allow idle time. So what happens is most of the time the collector is not working. So just you don't need to cooperate with him for long idle times. When the collector wants to start working, it raises this flag. It does the handshakes, with each of the mutators. It's called the handshakes because this flag, responding with the flag is like shaking hands with the collector. So the collector shakes hands with every program thread. And then when you know the collector is not working, you can just run without any cooperation. When the collector starts working, you start to cooperate. So you do the handshaking, and then you know the collector is starting, and then you start doing the write barrier. You remember we do a write barrier, we shade, maybe the new guy or the old guy. So Dijkstra says you shade, each time you write, you shade the new guy. DLG will say, let's shade the old guy. It will work. We'll see. But before the collector is running, you don't need to shade. You don't need to do anything. You just run without cooperation. Yeah.
אז בעצם איך מגיע רק עם הנוטיפיקציה של המוטיבציה, כמה מהשאלה.
Yeah, I only care if this happens. There is one long. This is not good for me. If this happens now, the negation of this is that no one has a long write. Each of them just has to make sure they don't have to be coordinated between themselves. Just each of them separately has to make sure there is no long write from the previous collector to the next one, and this is all that I care about. Now, but another thing is that once everybody has noted that marking is started, they also start doing the write barrier. Before that, they don't need to do the write barrier. This is like an additional benefit. I can run idle times because I know the collector is not working. If the collector will start work, it will have to handshake with me just in order to start the collection, but that will tell me that now I need to do the write barrier. So the second good thing about this handshake is that before I get the handshake of the collector, I can just do nothing. I don't need to cooperate with the collector. Once I respond to the handshake, I know that the collector is marking, and I need to cooperate and tell him whenever I change a pointer. Yeah.
יש לך פה את הדוגמה של טיימינג 3 מהמצגת.
Right.
הדוגמה הזאת אז היא בסדר מבחינתנו.
So let's see. From correctness point of view, I worry about the write starting in the mark phase and ending in the next mark phase. And this is clearly not happening here. But in terms of what the collector actually checks, So it at some point it raises this flag and it wants all the threads from that point between these 2 points to finish a write. So let's see. So this guy finishes a write. This guy also is not in the middle of a write. All of them are okay. So you just check one by one that it's not in the middle of a write. And that is in practice done by a handshake. But you can see, if you look at what's happening, you can see that there is no lingering write that goes until the next marking phase. Okay, any more questions? Cool, so we have this handshake, and so when the collection starts, each thread responds. So it first responds, and now it also starts execution of the write barrier, and it also shades its own roots. So in the world, in the real world, the roots are also the local variables of the program threads. And each program thread has its own local variables. And this is the way to shade all the roots. So whenever a thread, a program thread, responds to the collector, collection is starting, it also shades the roots of itself. It tells the collectors, these are gray objects. These are reachable from the roots, and you have to trace their descendants. So this is so when the collection starts, each thread responds when it's not in the middle of a write. It starts running the write barrier, and it also tells the collector what is directly reachable from the roots. So this is how it happens. And so DLG uses shade and change, and they can use many threads. It will not be a problem. And they use a handshake before tracing starts, and that gives the correctness of the collector. Okay, so how do we do this write barrier? So we don't want to have write barriers on local variables. If I write p equals this node, and then p goes to the next node, and p goes to I have this local pointer p, and it changes all the time, while heap pointers do not change that often usually, but my local pointers, they change all the time. I traverse some linked list, I do something. I do not want to burden these very often changes with a write barrier. I don't want to make them costly because they happen a lot. So most modern collectors, they avoid a write barrier on the local variables. And this is going to be problematic because I may miss some objects like that. So do we miss live objects? Okay, so we have this pointer change. And if the parent is a root, we do not cooperate with the collector and we don't shade the target, right? So do you think it will work without it? It will not. So the way it's very easy to see that it doesn't work. So suppose at some point T1, there's a thread T1, and it scans the roots and starts the write barrier. This is when it responds to the collector, marking is starting. T1 is a thread, and it says, I'm responding, I'm not in the middle of a write. You can start the marking. I'm also shading my roots, and I'm also starting to do the write barrier. I will shade the new object when I change the pointer. So let's see. So T1 does that. It shades whatever is reachable from its root. I do this for roots of T1, its local variables. So I shade this, and then the marking can start. Now, T1 writes another root to A. Now, when you change a pointer, the new target of the pointer should be shaded. But we don't have write barriers on the roots, so you don't shade A. This is a modification of T1. You don't shade A because it's a local change. Okay, so this remains white. And now T1 eliminates the pointer from B to A. Okay, so if I go back, T1 puts this pointer and removes this pointer. So now there's no pointer from B to A anymore. And This is a pointer in the heap, so the right barrier does work on it. So we need to change the new target of this pointer, but the new target is null. So there's nothing to gray, nothing to shade. Like the old referent was A. It would have been nice to shade it, but we shade the new target, and so there's nothing to shade. And now we're in a really bad position. If the collector finishes, it goes to a gray object, marks its shades, its children, which are none, and makes it black. And then there are no gray objects anymore in the heap, and the collector may finish and we'll have A reclaimed. So this is really bad. Yeah.
כאילו אומרים שזה בגלל שזה לא קל, כאילו זה...
No, I'm not worried about not reclaiming objects. I'm worried that I'm reclaiming this guy and it's reachable. So the program still uses it and I'm going to reclaim it and allocate it for some other purpose. And there's going to be chaos in the program. You know, I'm going to lose the semantics. It's just not correct like that. So this is a real worry that some reachable objects will be reclaimed. And this is what happens here. So I cannot just say, I will not follow, local changes. So the first thing you can say here is, I lost this pointer and maybe I should shade the old object instead of the new object, and then I will save A, right? This is a first modification that you could do. So let's try that. So I now shade the old value, and I will show you a different example. So this is the old value. When I change a pointer, I shade this, not this. It will solve the previous example, but I will give you a new example that it doesn't solve. Okay, and we're going to we'll try to solve this one by one, and we'll get more and more complicated examples. So until you say that you cannot anymore, and then I'll stop. Okay, so we'll see how much you can take. Okay, so the first thing we're trying to do, we'll do the old example will be good if we just shade the old one. And I'm just now trying shading the old object and see if it works. So here's an example. So we're shading the old value. T1 scans the roots and starts. So T1 responds. So it then shades whatever is reachable from it. And then it starts to do the right barrier. T2 has not yet done so. So each thread does that in its own time when it's out of a write operation and it responds to the collector. It shades whatever is reachable from its root and starts the write barrier. So this is where T1 responds and this is where T2 responds. And in between, I'm going to do something. Okay, so T1 is responding, it shades B, and it's now doing the right barrier, everything is fine. Now T1 is going to move its local root to A, okay? It already shaded its root, now it's going to move his pointer. When you move a local pointer, no right barrier is executed, so you don't gray anything. Okay, so it moves to here. And then T2 eliminates this pointer. So T2 is not yet has not yet responded to the right barrier to the collector. It doesn't know that there is. It thinks there's idle time. The collector is not yet working from his point of view. So when it does changes, it's going to erase this, but there will be no right barrier because it's idle time. You don't need to do a right barrier, right? It hasn't responded yet. So here it removes this and still not doing the right barrier because it has not yet responded to the collector and it doesn't know that it's marking. So it doesn't shade the old value of this pointer. Okay, now T2 responds to the collector, shades its roots, which are already shaded, and starts to do the right barrier, but it's too late. What you see here is that no one is going to, the collector is not going to notice A, because when T1 was shading its roots, T1 was pointing to B, and when T2 is shading its roots, it's also pointing to B. Both of them are graying B, but none of them is telling the collector that A exists, and the collector doesn't know. So what you see here also is that A will be reclaimed, which is bad. So what can we now do? What do you suggest? The problem is that, T2 erased this pointer and it was not yet doing a write barrier. Yeah,
When the first thread starts the right barrier, everybody else also has started. Then you know that everybody's doing the right barrier.
right. That's an excellent intuition. We do not want to let them cooperate all of them at the same time because that would mean stopping them. But what we would do, we would do two handshakes. The first handshake say everybody starts the right barrier, and the second handshake everybody will shade whatever is reachable from its roots. So that's the way to go. So we'll just use two handshakes. The first, when I respond to the collector the first time, I start the right barrier. When I respond the second time, then I shade all that's reachable from my roots. A question? Yeah. Okay. Yes, everybody starts to use the right barrier when they respond to the collector in the first part. But each one of them does it in its own pace, right? If you remember all the drawings, there's some guy is finishing a write, it responds to the collector. Another guy is finishing a write later, it's responding to the collector. And each of them responds at a different time. And what this does, it lets T1 responds here, T2 responds later, and in between, these are doing something, which is becoming really wrong. But the response to the collector is at different points in time, and the start of the write barrier is a different point in time for different threads. And what we want to do, if we use two handshakes, is we say, first we make sure that everybody is running the write barrier, and only later we let all of them shade the objects that are reachable from the roots directly. Yeah, and yeah. Write barrier, all it does is when you change a pointer, you shade, one of them. This time we're shading the old value. That's not stopping. That's just adding one instruction to your write. Each thread has its own, world in a way, and it is maybe now in the middle of a write, right? So you can think of a timeline. So one thread, maybe T1 and T2. One thread, it responds first. So it has a write, and then it responds, and then it starts doing the write barrier in its next write. Thread 2, maybe when the first guy responds, thread 2 may have this, long write. It cannot respond in the middle. It will respond later, and the collector will start tracing only after all of them respond. But each of them respond later, and then maybe he has another write. So both of them, after they respond, they start doing the write barrier. But one may be doing the write barrier while another is not. I can, linger, make it longer to make it look, there could be a write where one guy is using the write barrier and the other guy is not yet using the write barrier. Right? After they all respond, I know they're all using the right barrier. And this is the suggestion here. Let's do two handshakes. Let's get them all to respond and do the right barrier. And only later, they will respond and shade the roots. And now I know them when they're shading the roots. Everybody is using the right barrier. So it cannot be that someone will shade the root after, one guy is not using the right barrier and disconnecting this. Okay? Okay, so we're doing this now. We're going to get into an example which is a bit more complicated. I will explain it. And maybe after that, you will ask that I will stop with these examples and fixing. But I just want to say that it's important for me to show you that things get complicated so that you will understand. You know, Dijkstra had like this simple thing, and he said, wow, we've fallen into all these traps, and things went wrong, and they were not correct, and so forth. And Doligez and Leroy published something that was actually wrong, and Doligez and Gonthier fixed it. So I want you to see how it gets more complicated. So now we have two handshakes. In the first, I start the right barrier. In the second, I shade the roots. And let's see what goes wrong. So what's going to happen is I will have one thread that wants to write B into A, into the pointer in A, and another thread that wants to write C as the pointer in A. And I will let them do it in an interleaving that will make it a problem. So T1 is already responded in the first handshake to the collector and is now running the right barrier. T2 is also running the right barrier. T2 did not yet shade its roots, so it will shade the roots here. Okay, so I have T1 running the right barrier, T2, both of them responded in the first handshake, they're running the right barrier, but T2 is responding here to the handshakes that says shade your roots. T1, I don't care. Maybe it does it after or before, I don't care. I don't... Yes, you can think of it's reachable, but say even reachable directly by the roots, it doesn't matter. But A is reachable. That does matter, and the program can only make changes in objects that are reachable when they do the change. So okay, so T1 wants to write B into that pointer. What do you need to do to do that? You first shade. So you mark the old value. I look at what the pointer is pointing at, and I shade it. In this case, it's null. So this pointer is pointing at null. I need to shade the null, so I do nothing. And then I'm going to let it wait for a long while until it actually makes it point to A. Okay, and here I'm going to do bad things in the other thread. Okay, so thread one is easy. I shade, I wait for a long while, and then I change the pointer. Now, what is going to happen here is A is going to change from null to B, and the change is going to happen without any further shading. And I'm going to use this pointer to hide an object from the collector. So I'm going to put it here, and no one will shade it when the pointer moves to B. Let's do it step by step. So T2 is he has a local pointer to C. C is currently reachable because it's pointed by roots of T2. And it will remain reachable all the time, but the collector will not be able to notice it. This is the goal of this example. Okay, so T2 writes C to here. Writing C, it marks it gray. It marks the old value gray, but it sees a null because that's what A points to right now. So it grays null, it doesn't do anything. And then it just changes the pointer to point to C. So C is now pointed by the roots of T2 and by A. Okay, right now the collector will still see it if it traverses everything. But now what T2 does, it removes it from its local roots. So C is only referenced here. And while this happens, C is still reachable. It's okay, it's reachable from A. But now T2 does not hold it in its roots. So it's going to respond to do the second handshake, respond to the collector, shade its roots, but not C. C is now not there. And after shading its roots, it's going to get C back to its roots. So it's going to look what's pointed here and get it back to its roots. So while it shades the roots, C is not there, but before and after it is there. So before shading its roots, it puts C in this pointer, and after shading the roots, it gets it back from this pointer. So now C has not been shaded as a root of T2, but it is a root of T2, and it's still alive. And it was just here, it was hidden here in the heap. And now I'm going to let this T1 do its change. So it's going to change this pointer to point to B. And no one is going to shade C. It is reachable from T2's roots, but no one in all this course of events, no one has shaded C. And the thing is, it was like we were hiding it from the collector here. It was always available from my roots. I'm T2. It's available from my roots. But before I tell the collector what my roots are, I put it here, I shade my roots, and then I take it back. So I don't shade this when I shade my roots. And this write is responsible for removing C from this pointer. So when this write comes, it's going to point this pointer at B, and C is not going to be available from that pointer anymore. So it's like we've hidden this C in the middle of T1's right. T2 has hidden C in the middle of T1's right. Yeah.
But if you do a pointer as B, don't you have to shade C because it's the old one?
But I don't know it. When I started, all I know is what I see. Yeah,
But if you
right.
did start a new lookup, you would be shading.
Right. Intentionally, I did this long write where C is hidden and I don't notice it, and then I change the pointer. If this changed, if this was completed immediately and a new one would start, I maybe would see C and I would mark it gray. But this is the way it goes, and so I don't see C. And yeah,
This A but T2 doesn't have any.
yeah, maybe it has other roots. We don't care, but it doesn't have C. Suppose it doesn't have any roots after this. So I just look at A dot pointer because this has not happened yet. This happens first. If I look at this pointer, it still points to C. A is reachable. You mean if I have no other roots? You have other roots. Maybe A is a root of everybody, of T1, of T2, of T3. If everybody can see A, I don't mind. I mean, it could be more complicated. Maybe I have to get to it somehow. But say everybody has A in the roots. So when I say here, I mean a pointer, a specific pointer local that points to C. I nullify it. I have another pointer to A, and I can get to A. You're right. Yeah. Okay. So are you convinced that this is a counterexample? This is 1, 2, that it's beginning to be complicated, and 3, that you don't want to see more of these. If you're not, we're going to continue. There is another one in the slides. Okay, I see yes in the... Okay, people are nodding. So another try is I can say, I can shade both old and new. This will kill this example. But I can give you another example. If you want, you can look at the slides. There is another example that will do this in the same manner. And so what DLG do in the end, they actually add a third handshake. And between the first and the third handshake, they shade both the old and the new, and then it becomes correct. But it's not easy to get to that, and it's clear why people do mistakes in this. Okay, so to summarize, we have 3 handshakes. One telling the mutator to start the right barrier. The second is kind of just nothing, cooperate to make it correct. And the third is where the mutators mark their roots. They shade everything that's reachable from the roots. And this works with 3, and shading. So between the first and the third handshake, you shade both old and new. And this works. This,
Achieving both old as and new doesn't work.
no, this will work also if you always shade, but this is like work you don't want to do. Like in terms of time, you can think there is like the marking phase and the sweeping phase and the long idle phase. If you always mark everything, then it works, but you want, so this is the marking phase, and there is this, the handshake phase, which is really small between the first handshake and the third handshake, and only here you mark excessively. So usually everywhere you don't mark more than you need, and marking the old object is good enough whenever you're not between the first and third handshake. Okay, so this is the DLG. We will not fully talk about all parts of the algorithm. We will not. We only discussed major issues in the design and tried to give the feeling that there are problems, and it's difficult to get it right in terms of concurrency. When you have all these constraints, you don't want write barrier on the local variables. You don't want to stop all the threads at the same time. So the proof that appears in the paper cannot be taught in class, and producing a simpler proof is a project. Probably no one will do it. Soon I will explain why, but this is the proof in the paper. You'll probably not want me to go through it, and it's not very friendly. It's more for a computer to check that it's okay than for a person. And but the properties of this collector is that it's on the fly. You don't have to stop all the threads at the same time. There is no write barrier on local variables, which is important for efficiency. It's good with multi-threading, unlike Dijkstra that could only use one program thread. This can work with many threads. Handshakes and the write barrier overhead is small. It's not large. And this basic collector was made practical in a series of works. Like in IBM, it became the production collector. And a modern version of the algorithm became part of IBM production collectors. I just want to say that it was complicated. And what happened was that when it went out, so there were the designers who were able to deal with it. And after that, it was sent to some another group in IBM who was responsible for maintaining it. And it was very, very difficult for them. And whenever there was a Java change in the operation, Java extends, whenever there is a new JDK, new features of the Java programming languages, you need to change the collectors. And it became too difficult to maintain it. And then they moved to a lot simpler collector, which we'll talk about in the next hour. But this is kind of a lesson. You can do very complicated things that are very efficient and give very small pauses. But in the end, you have to be able to let people maintain it. And then, so it should be possible to understand it fully by those who maintain it. So in academia, we can do this, but in practice, there are limitations. So to summarize, we went over Dijkstra. We did a full proof on like a graph. The proof was not on the code. It was on a graph that represented the algorithm. But it was theoretical, only one program thread. That was not good. DLG, on the fly, there is a full proof. It's less abstract. It goes with the code, but it's too complicated to do in class. It's practical. You can use several threads, no write barrier on the roots. Everything works well. And the extensions of that went on to become production JVMs. Okay, so this concludes the Dijkstra DLG talk. If there are any questions about that? Okay, cool. So let's take a 10 minutes break and 35 we'll meet. This we're going to talk about the mostly concurrent collection. This was invented by these three really important researchers in those times. It was done in Xerox PARC. Xerox Sparks, like I often talk about IBM as the leading research industrial company in the 90s. Xerox Spark was like the most advanced company 10 or 20 years before that. It was now you think of Xerox, you think of copying papers, right? This machine that copies things. But Xerox Spark was amazing at the time. They invented Windows. You know, before them you just typed on these terminals, and they invented Windows. And um, later Microsoft adopted it, and then Apple adopted it, and the Xerox was where the best research was done in industry. And these three people invented this garbage collection. Bohm, we'll get to him. He did a lot of work on garbage collection. And then 10 years later, this was done in Sun Oracle for Java. And this was done in academia in Japan, and this was done in IBM here in Haifa. So it started to become a very important collector. And for a while it was like the collector of choice in all companies. It reduced pause times, which was enough for that time. It wasn't perfectly short times, but it was good enough, and it was simple. So let's see how that works. So we want to reduce the pause times without affecting the throughput too much. This is our goal. And the idea is that we want to run most of the collection concurrently. And so, the problem is that the heap changes during the collection. But how much of the heap changes, right? We want to run and search for reachable objects. And sometimes the program is going to cheat us. It's going to move a pointer and we're going to miss an object. But most of the heap we can do very well by just doing it concurrently with the program, and we'll find most of the reachable object. So we do that. We start by running the collection concurrently with the mutators, but we have to know if we missed something. And the way to do it here is to say we trace again from all the things that we traced but were changed. Okay, so if you look at this, Dijkstra said, let's notice, if we do a pointer change, let's notice the new object. We marked it, we shaded it. And DLG said, let's notice the old object. And mostly Concurrent says, let's notice the parent. And there will be, so these are the three very famous write barriers. Like this is called Uaja, this is called Dijkstra, and we will have a talk about all the different write barriers. There is one that is a bit more complicated and is required for reference counting, and we'll see it. It's a nice one. But there are all kinds of write barriers, and the mostly concurrent one looks at the parent and he says, if I change a pointer, I will remember this parent. So maybe I marked it, but now it has a new child and I need to trace it again. Okay, this is the main idea here. So I trace again from all these objects. The way I do it is I have a card table. If you remember from generational collectors, we had card tables where we marked any pointer that was changed. We marked the card on which the pointer resided. So here we're going to do the same. You change a pointer, you mark the card. You have maybe a card of 512 bytes of memory each card, and then you have a bit per card saying whether it was modified. It's called dirty. Like in generational collector, a card is dirty if it has been modified. And so we're going to have this card table, a small card table, and this is really a very efficient write barrier. When I do a change, I just mark this bit for the card, then the collector will check it later. So this is the algorithm. I just run marking concurrently, ignoring the fact that things change in the graph. And I try to mark as many as I can reachable objects by that. And while I do that, the program runs the write barrier, whenever a pointer modified, its card is made dirty. They dirty the card of this, where the pointer was changed. And after I finish tracing whatever I managed to trace while the pointers are changing, I go into a card cleaning phase. What I do is I look at all the dirty cards, and whenever I see there a pointer that was traversed previously, I traverse it again. I check the child again. Okay, so all marked objects, I go and check their children again. This is so what's the problem with that? Right. First of all, I will do redundant work because maybe they haven't, something in the card has changed. But even, if I do, not even, yeah, this is a good thing. This is a good shortcoming of this. But what I want to emphasize on top of that is that I don't know that I will ever finish. Right? Because while I'm doing these checks on things that I've already, traced through, now the program comes again and dirties more cards, and I will have to go to them, and then it will dirty more cards. So as long as all of this is done concurrently, so at some point, so let's focus on card cleaning. So for each dirty card, I cleared the dirty bit. I'm going to test it now. I'm going to retrace from all marked objects on the card, right? And I always check the roots again. I could have, dirty cards for the roots, but they're always changing, so it will always be dirty. So whenever I do card cleaning, I check what is reachable now from the roots, and this is alive. So that I always do. Roots are usually a small set of pointers that I don't mind checking again. And the problem is I could do cleaning again and again concurrently, but I will never end because there's always going to be more dirty cards. So in the end, when I think I've discovered most of the reachable objects, then I stop everybody and I do a card cleaning while the program is halted. So the program does not dirty more cards, and I know that I'm going to finish. So I do this card cleaning again while the program is halted, and then I'm done with the tracing. I can let the mutators resume, and then I do sweep. I can do sweep concurrently. Sweep is usually not a problem. I don't care if pointers change while I'm sweeping. I'm sweeping, I'm looking for things that are not reachable, and clearly the program cannot touch them. This is just garbage. No one touches it, and I have to tell the allocator it can use this space. So forget about sweep. It's not really challenging, and I can do it outside. But the tracing. So I first do it as if no one disturbs me. It is going to go wrong. I look at all the changes, all the places where changes were made, and I trace them again. If I trace it before, I trace it again. And of course, if I find something that is white that I haven't noticed, I trace through all its children, all its descendants, and I mark them too. And at the end, after I do this, I could do this many times. Usually it is done once concurrently, and then program is stopped, and I do it once while the program is stopped, and then the tracing is bound to discover all reachable objects. Yeah. Right. Right. So the question is, what do I care to do this again and again and again? It doesn't disturb anyone. So first of all, I don't get progress until I do sweep. I don't get new objects that I can allocate with. So I want to get to sweep at some point, and when I get to sweep, I must know that I've marked all reachable objects. So I need to finish at some point just in order to make progress and get some new objects for the allocator. So this is a reason to at some point that I want to finish the trace. But also, when you say it doesn't cost me anything, it assumes that I can do it concurrently on some core that no one uses. And this may be correct on my laptop, but it's not correct on a server because there's always something to be done, you know. But I'm not talking about the Google, you know, cloud where everything is all the time serving clients. But even if you're looking at a reasonable business, you know, things are happening, and so you don't get it really for free. You let the program run without many interruptions. This is the main goal to let it have small pause times. Until this is the pause times. When you stop the mutator and you do the last card cleaning, this is the pause time that the user feels. And so it's not really free. You feel it. Okay. The sweep you cannot start before you're completely done with the mark. Because the sweep assumes that if something is white, it's unreachable and you're going to reclaim it. If you're not sure you're done with the marking phase, you cannot run sweep. No, but this is the problem. You don't. So in general, in garbage collection, you think, let me identify those that are not reachable, and then reclaim them. But usually, garbage collection goes the other way around. I identify those that are reachable, and I reclaim the others, right in Mark Sweep. And so until I finish identifying all those that are reachable, I cannot start reclaiming because I don't know which are unreachable until I have the full set of reachable objects. So I must completely finish the mark before I can start sweeping. Yeah. You're saying let's go the other way around. Let's give up this. Just do this. You know, let's do the first race and then do this. Right. So this is an evaluation, right? That of course depends on the benchmark that you run, computer you're running off. But I think in the industry there were several companies running these algorithms, and all of them came to the same conclusion that it is best to do one of these. If you don't do this, what you have is you have more cards to clean, and the objects that you find that you haven't found before, you really have to trace all their descendants, which takes time. And you really don't want to do all that while the mutators are stopped. You want to get here when you have dirty cards to check, but most of them point to objects that you've already marked. So you really don't have to spend a lot of time here. This is the valuable time, the time you want to reduce. Yeah. Yeah, you're asking for the race between sweep and allocation, if it happens also here. Yes, you have to worry about that in all the concurrent sweeping algorithms. Um, we we did this kind of clumsy solution in DLG. In your homework, you'll do a really elegant and nice solution, which so I can, well, you'll see it. It's really nice, and people just use that in real collectors. And so it is doable. You can do it in the clumsy way we did, but there is a nicer way to do it, and you need to do it whenever you have a concurrent sweep. You're right. Yeah. Okay, so this is the algorithm. More issues, new objects are created black as usual because they have no children and they're alive. We can do that. Now let's look for correctness. Why is this correct? So if I have if I have some reachable object, right, and right, some reachable object at the end of the collection, right, when I do the stop the world, and suppose it is reachable by some path of pointers. At the end, there is some route. So there are two options. One option, and let's go back on this path as we like. So one option is that the traversal managed to go through it before any modification happened. Like even in the original in the original concurrent tracing, then of course I will find this if all the edges were traced before any modification happened. Now, if some modification happened, let's look at the last. Suppose this was last modified. So I will go through this as they were in the original view of the heap, but this was changed. It was like modified from here to here at some point, and I didn't see this. I looked at this. Then this card will be dirty, and in my some card cleaning, I will find this pointer, and I will go through it, and then I will continue and find this reachable object. So I will find all the objects that are reachable at the end of the collection. So correctness is fine. Progress, if there is something that is unreachable before I start the marking, there's no way that I'm going to mark it, right? What do I mark? I mark things that I feel are reachable by traversal, and then things that become reachable when I change pointers. But if something is not reachable from the start, there's no way I'm going to mark it. So I will do progress. I will reclaim objects that are unreachable in the beginning. There may be some floating garbage. So maybe I will mark an object and then a pointer will change and it will become unreachable, but still I marked it. And so I will still not be able to reclaim it. That's fine. But in the next collection, I will free it as usually. Trade-offs. I could do more phases. This is something that you already asked about. I could do more phases of the card cleaning. I could do fewer phases, just not do anything. But this is the best as it was found in evaluations of this collector. Okay, so overall, most of the work is done concurrently with the program. I managed to mark most reachable objects. There's short stops in the end to clear and scan all the dirty cards. And so I have short pauses. This is not like the DLG that has really short pauses, but it reduces the pauses. And the overhead is this write barrier and the fact that I have to scan again, like you said. I scan repeatedly edges, like pointers that were modified. Okay, so I used to bring here a guest lecturer from IBM, this guy, Yoav. He would come and I thought it was really nice. It would give kind of industry point of view on how people who design collectors do that and what they worry about. He studied in the Hebrew University. He did his undergraduates and the masters in Jerusalem, and then he came to IBM, to the research center, and he worked there for a long while, and then he moved to Microsoft, and he's now many years in Microsoft. They did this, so they had like, I was also involved, but there were like 3 papers, reporting this collector. It was in IBM production since 2002 when DLG went sour and it was not possible to use it. They brought this collector and it remained for a while there. I don't know until when. Now there are new collectors. We will talk about them in the end of this course. Okay, so I used to bring him, and for many years he came and he gave a talk about this collector. And at some point he said, I'm not doing this anymore. I don't know what's going on in this area anymore, and I feel uncomfortable talking about things that maybe I don't know. So I just took his slides and I talk a bit about this, but I already see that we don't have enough time to talk too much about it. I will start with it for like 5 minutes to try and give you some feelings on how industry looks at it. And then I will go back to algorithmic issues, how you improve this collector algorithmically. Okay, so the mark sweep compact that they did is the collector. So you have to do compaction in real life. You cannot just leave holes and get it all fragmented and just use more and more memory. You have to do it. You have to do compaction. And so they do mark and they do sweep and they move all live objects, as we know compaction does. They use bitwise sweep, which you've already practiced, so I will not go into that. Um, and here is the picture that he drew. So you have the heap, and you have roots like stacks and globals that point into objects in the heap. And then there are pointers inside the heap, and you run marking, and eventually you see which objects are reachable. These are the blue here, as opposed to the white that are not reachable. And then what sweep does, it builds a linked list between all the spaces that are available. Because they are running bitwise sweep, there will be small spaces that will not be added to the free list. And this they call dark matter. Okay, very physical, but they liked it. It's dark matter. You don't see it, you don't know what it is, you don't use it. Okay, this is from due to this bitwise sweep. And then you compact, you move all the blue objects to the beginning. And what you see here from the real world is that there are some objects that you cannot move. These are unmovable objects. Maybe you've sent pointers of them to another programming environment and you don't control them anymore. You have to keep them where they are for any reason, and they remain. So when you do the compaction, you have to deal with it. You have to, sometimes even when you have compaction, because things do not move, you'll have things that are not compacted to the beginning. Maybe these unmovable objects will create some space you cannot use. These unmovable objects will stay somewhere where you don't want objects, but this is real life. This is how it works. So from their measurements before they did this collector, marking took 83% of the time. So really most of the garbage collection time was used for marking. Sweep was almost nothing. And stopping all the threads together took like 3% of the time of the collection. So they really concentrated on marking. And in the beginning, they left sweep in the stop the world phase at the end of the marking because it was so small that they didn't care about it in the beginning. So marking was the thing that they targeted at doing concurrently. And then let's look at this, how they worked it. So incremental, concurrent, and parallel, their collector. So first of all, incremental is like we did with Baker. Whenever you do an allocation, you contribute some time to the collector. So there is a parameter k, you allocate a word, you scan k words for the collectors. So this is the incremental. So you see each thread is contributing time to the collector. Concurrent means that the collector runs concurrent with the program. So you see, like the collector is the yellow thing and the program is the green things, and this is just the time passing in each of the four cores here. Sorry that I didn't introduce it, but you've seen similar things. So here you have the collector working concurrently with the program. That is called concurrent. And also there is a collector with collector running in parallel, and that is called parallel garbage collection. So we have here incremental, concurrent, and parallel in terms of what you have to design. And also, when collection was not going fast enough, they would open a full thread doing concurrent work on finishing the collector before the heap gets exhausted and you don't have space to allocate. So this is the way they render collector. Question, yeah.
When you showed the for the market sweep and stuff, so for the market and we have like free garbage that you use the
Ah, okay.
they also show the statistics for the amount into the time mark that you'll probably that's
Floating garbage is when you don't have an accurate mark, right? If it doesn't matter if it's a fish, if it's long or short. Well, maybe it does because if it's long, you have more chances to miss objects, to mark objects that will later become garbage. Yeah, we will talk a bit about this.
if it's more important for the mark face to be shorter and you don't mind the floating garbage, then maybe there's something there you could
Okay, so I see that I will. Maybe I should read. No, no, I think, okay, this is one of the points that he talks about. So let's maybe jump to it and just talk about that. I think much of it is okay. This is what I wanted to show in relation to this. So you can control this k. You know, when you allocate a word, how much time you do for the collector. Okay, and it will determine. So if you do a small amount of work for the collector, so this what is printed here, depicted here is this is the time, right? The yellow thing is the stop the world phase. So here and the program is green. This is and this is like the height is the CPU time. How much is given to the collector? How much to the program? So in the yellow thing, all the CPU time goes for the collector. The red thing is like the CPU time given to the program, and green is for the program, red is for the collector. So if you choose, so first of all, this is stop the world. So you just stop the program, run the collector, and then run the program. This is what we started with. Now, if you have a mostly concurrent collector, you can decide if you let the program does a small amount of work for each allocation or a large amount of work for each allocation. And what happens is if you just do a small amount of work for each allocation, then each time, then most of the CPU can go for the program. You don't bother the program too much. Unlike here, where in this time where the collector runs, most of the time goes to the most of the CPU goes to the collector. But this takes a lot longer because while you're running the collector, more cards get dirty, and maybe you also have more floating garbage, and so this takes a lot more time, and maybe you run it all the time between the stop the world collection, and it turns out that this is a lot better for throughput because this is so short and you finish it quickly. It doesn't take a lot of the CPU. If you do it very like that, the program does not feel the disturbance, but it takes a long time, and from the CPU it takes a toll. You really need to spend a lot of CPU. If you just look at the space here, there's a lot more space here than here. So that is something that he wanted to stress, and they choose it and they can control it and decide you do more work for the collector or less work for the collector depending on how much you still have heap available for allocation. If you feel the heap is getting smaller and smaller, the free space, then you start moving into this kind of thing. If you have lots of space available, you can run this thing that doesn't disturb the program. So it's kind of a decision you can make, and they kept this parameter dynamic to be able to control what's happening. Okay, so I want to jump back to algorithms, and maybe at some point I will do. I will do this towards the end of the class, but I feel maybe because of the English we're doing a bit slower, and I do want to finish it. I mean, it's my fault, not yours. I'm maybe speaking a bit slower, but let's go back to algorithms. So let's look at this. So in IBM, when we were doing this, we found like two simple algorithmic modifications that made a difference. And let's look at them. So the first thing, there is an observation here which also bothered you while I was describing this. You were saying there is repetitive work. I trace something and then I trace it again. And so if a card is dirtied, then reachable objects on this card are going to be traced again. And this is going to mean that there is repeated tracing. And I want to reduce that. What can I do to reduce that? If you have an idea, it's not a very, so it's surprising this algorithm existed for maybe 10 years and no one suggested better algorithms here, but the modifications are really not that difficult. Right. You could, so basically you're saying make the card smaller so you'll not have to scan a lot, but still anything that changes, you still have to trace again. Even if you don't have this inaccuracy because the card is large. And I want to reduce that. Yes.
Maybe we can remember for the cards what we already traced and hasn't changed, or is it against the whole idea of the card?
What was trace and what hasn't changed? No, but that's the same suggestion. You want to only trace things that were changed and not others. But even if you just trace things that were changed, you do a repeated work. So I want to not to scan twice this thing. How can I not scan it twice? I not scan it twice. Yes, that's exactly what we want. But how? Okay, cool. Yeah, that's the simple idea. So what I'm going to do, I'm not going to trace through dirty cards. I arrive at a dirty card. I mark the object as reachable, but I don't trace. I don't go to its children. I know that when I clean the card, I'm going to look at marked objects and look at their children. Why should I look at them now? You will look at them when you get to the card during the card cleaning. So I don't want to look at the children. So I save all the tracing. I do not trace objects that are already on dirty cards. Okay? Yeah. Excellent. Okay, we will. So there is a disadvantage to this. If we leave stuff to the card cleaning, then we miss. We'll have longer pauses. So we'll have another modification that will help that, and so we'll save on both things. But this is really the first thing. And so how do we do this? So moreover, on typical benchmarks, we have some hot objects that keep on changing all the time. And if we trace all the time, we have to trace them the first time, second time on card cleaning, and third time on the, stop the world card cleaning. And so all the time we'll have to trace them. And many times they reference objects that become garbage. So we trace them 3 times, and the first 2 are going to be for objects that we could have reclaimed if we didn't trace in the beginning. So this is really nice. So I don't trace through dirty cards, and I also win less floating garbage. So because I don't trace stuff that later becomes unreachable. Okay, so while tracing, if I get to an object, I check if it's on a dirty card. If it's on a dirty card, I just don't trace it. I mark it and I go to the next, to my mark stock to find another gray object. So the advantages is that I have less tracing work and reduce floating garbage, which is great things for me. And so the throughput becomes a lot better. I don't spend time on garbage collection, but the disadvantage is that I get higher pause times, like you say. This is not good. I wanted to save on pause times. Okay, so I want to do another thing that will reduce the pause times. I want to have fewer dirty cards. So the observation here, what you notice is you need to dirty a card because you want to say, I've traced here and something has changed, so I have to trace it again. When do you not need to dirty a card? Like there is a case where you just don't need to. You come to a card, you change it, you change a pointer, but there's no need to dirty this card. When does that happen? Yeah? What? For, correct, but the opposite. If I change, right, if I change the pointer for someone who is white, right, that hasn't been traced, then I don't need to tell anybody. What I need to tell someone is, you have traced through this, and now you need to trace again. But if you didn't see this object, you haven't traced through it, there's no need for you to test again. You will come to it after I change my pointer, then you will trace it then. So I don't need to dirty this. If I dirty the card, all the other objects are going to be traced again. It's not good for me. I want to avoid dirtying if I don't need to dirty cards. So I don't need to dirty a card if nothing is traced on this card. So I'm not going, and when I modify a pointer, I want to not go through a large test, like a costly test that I will need. Was this specific thing marked or not? I just look at the card, and if the card, there's nothing on this card that has been traced, so also the object that I'm changing has not been traced, and this is like a conservative test, which is very quick. I'm going to have another bit per card that is going to say, have I traced anything on this card? And if nothing has been traced on this card, there is no reason to make this card dirty. Okay? So the second improvement is that I can even undirty cards. So what I want to do card marking as let the program do card marking without any test at all. If I make the program all the time check if the card was dirty, was it marked, all of that. If there is a branch in the write barrier, this is going to make everything too costly. And the program runs all the times, and there's a huge number of writes. I do not want to burden the program with such checks. What I'm going to do is once in a while, maybe 3 times in the collection, I'm going to go through all the cards, and if it's dirty but nothing was traced on it, nothing was marked on it, then I'm going to cancel the dirty mark. This is the actual thing that I do because I don't want to spend the program time. I want to do it on collector time, which is a lot less valuable. So the program time is really very valuable. I don't want to overload the modification, the write of a pointer with more tests. So instead, I'm just going to, once in a while, undirty cards. I'm going to go over the cards. Each card that is dirty but nothing was traced on it, I'm going to remove the dirty card. I don't need it. It doesn't tell me anything useful. So there are 2 ways to do it that were done. Forget about this thing. We'll not have time to talk about it, but I just scan cards and remove the dirty bit if needed. So periodically, maybe 3 times during the marking phase, I will go to the whole card table and I will use a second card bit that says, was it traced or not? And if I see nothing on it was traced and it is dirty, I will just cancel the dirty bit. And okay, so during the scan, I undirty any card with no traced object, and it's very effective in. So it removes the dirty cards by 2/3. I remove 2/3 of the cards are dirty but have not been traced yet, and I can just remove the dirty bit, which reduces the pause times really nicely. So, of course, frequency is a parameter. How many times do I go and check the dirty bits? If I do it a lot, then I have better chances to find the card before it is traced and remove the dirty bit. But, the overhead increases if I do it too much. So 3 times is something that we did in the IBM collector. So advantages is reducing the work on scanning the dirty cards, shortening the final stop the world phase, which is really important, and significant. It had a significant impact on the pauses. The disadvantage is that you have to do it. You have to go through the cards. It takes time, so a bit cost on the throughput. Okay, so there's explanation on the implementation and tests. So if you look at it, this is done at tracing rate 1. So I didn't talk too much about tracing rate, but this is the K, where I decide how much do I help the collector when I'm allocating. And tracing rate 1, I do for each word that I allocated, I scan a word for the garbage collector. This is a small cooperation. So this is when the garbage collection take a long time, and we can see the effects of these improvements. So I'm saying, ahead of time that I'm looking at the place where we can influence the most. But the influence is significant. So this here you look at the throughput of the entire program, and it's amazing. This looks at how much you gain from so in percentage. This is just the two lines of what this takes and what that takes, without the improvement and with the improvement. But this is the percentage that you gain in throughput and how much the performance was improved. And when you have a large enough heap and enough threads, you get like 25% improvements in the execution time, which is really nice. Um, floating garbage, you want to see how much was it reduced. So this is the stop the wall. This is the blue one. This is how much of the heaps it takes. And the red one is if you take mostly concurrent without the additions, how much heap it takes. And the green one is with the additions, and you see that you almost get to the heap consumption that you would get if you really reclaimed all the objects. And this is like how much, okay, the optimal is with the stop the world, how much more heap you would get. And this is with these additions to the mostly concurrent algorithm. So you really get a lot. So base is just stop the world, collect everything, no floating garbage. Yeah, here, zero here is the heap. So this is the reduction in the heap residency, right? So mostly concurrent is the base. This is zero. And you reduce it by, I don't know, 22% if you use stop the world. You reduce it by maybe 18% if you use mostly concurrent with the improvements. So you reduce also the floating garbage, pause times reductions. So these are the maximum pause times and the average pause times. And here you see the reduction in percentage. So as the heap gets higher and more threads, you basically get to maybe 30% reduction in the pause times on average, and in maximum, I don't know, you could get to almost 50%, but depending on the heap size and the number of objects. Okay, so it was effective. So the conclusions is you have two improvements of this popular algorithm, and they reduce the repetitive work by don't tracing on dirty cards, and it reduced the number of dirty cards, and so the pauses, by undirtying cards that have no traced objects. And you get substantial improvement. You get throughput improvement, you get almost eliminate floating garbage, and you reduce the pause times. And we need to conclude. So most of the work in mostly concurrent is done by the program. We stop it for a short while in the beginning to start, in the end to do the last card cleaning. And we have short pauses, simple right barrier overhead, and we'll break here and have a happy Hanukkah. See you in 2 weeks.